Taylor series centered at 0, right? But I think on final exam I'm going to give you more general case. So I'm going to ask you to do Taylor series not centered at 0. That will becomes Maclaurin series, but rather centered elsewhere. And therefore, these are the two to remind you that you have to know how to do that. Everything else being the same, you just have to know that it's centered in a place other than 0. So here is the first one. And I specifically asked you to get the answer in two different ways. The first part, part A, use the definition of Taylor series. In other words, repeatedly take derivative. And it's manageable for this particular example. And then write out the general expressions. So this is doable. But then at the same time use other approach. And I'm suggesting here that you think along the line of geometric series. And then you should reproduce the same answer because we also have that Taylor theorem, which says that if the function within a certain happens to be equal to the sum of the power series centered at A, and then if it is a sum of any series at all centered at A, then it has to be the so-called Taylor series. Right? So if you somehow show that this function is a sum of any series centered at 2, then that series must be the one that you construct in A, right? Using a definition. So these two has to agree with each other. Okay, so could you spend some time doing this? This one is similar. Let me get started. So you'll have to do the part A. You have to do f of x is equal to 3 over 1 minus x, which means the 3 times 1 minus x to the negative 1 power. And then you have to do f prime of x equal to 1 minus x squared 3. There's no minus sign because you have one minus sign from the negative 1 power, another minus sign from chain rule, so they cancel out, so it's positive sign. And then you do this a few times to see a pattern. Next one, that will be 3 times 3 times 2, 1 minus x third power. Why? Because you'll pull out negative 2 when you use the power rule. And you also have to have a negative 1 because you have to use chain rule. And therefore, you don't have to contribute the negative sign. So it's still plus sign. F triple prime. You still have this 3 you inherited right at the beginning. But I purposely grouped this extra factor here from derivative. 1 minus x fourth power, and that is 2 times 3. So this extra 3 comes from this negative 3 power. But you also have negative 1 come from chain rule, and therefore you have positive 3. Next step, patiently take the derivative once more. Then you still have this 2, 3, and this time you have extra 4 because you have an extra negative 4 power. Extra negative 4 factor along with the extra negative 1 factor. Negative 4 comes from the power rule. Negative 1 power negative 1 factor comes from the chain rule. Right? So this is the next step. So you begin to see a pattern. So it looks like this one is, in general, the nth derivative of x looks like, in general, at 3 times. This one can be thought of as 4 factorial. this is 3 factorial, is 2 factorial, and so on. So in general, that must be the nth derivative. You should have nth factorial, and then 1 minus x to the what? N plus 1. Okay? And then you're supposed to evaluate it at the value center at which you have this Taylor series. So we are going to evaluate at a 2. All these at 2. So at 2, this one becomes what? 3 over negative 1. This one becomes f prime over 2 becomes 3 over negative 1 to the second power. Double prime of 2 becomes 3 times 2 factorial over negative 1 to the third power, and so on. And so in general, f to the nth power, if you f to the nth derivative that evaluated at 2, it should be 3 times n factorial, and then negative 1 to the n plus 1 factorial. Yeah? And so now that means that if you use this expression, that is perfectly fine when n is equal to 0. Is that right? Okay, so that works for 0 as well. Work for 1, n equal to 1, that's perfectly fine. 2, and so on. So it's this general expression, works perfectly for all orders, starting with n equal to 0. So let n go from 0 to infinity, and the Taylor series centered at 2 should be f nth derivative evaluated at 2 over n factorial and what? X minus 2 to the nth power. So this is the power series x minus 2. And so this is Taylor series centered at 2 of function n. And this, when n is equal to 0, 0's derivative simply means f itself. Right? Now anyway, you plug it in, you have this one. Therefore, I know that this numerator is just this guy here, but then you have to divide it by n factorial, and that get rid of this n factorial. Therefore, you get 3 over negative 1 to the n plus 1 power times x minus 2 to the nth power. And of course, it doesn't matter whether you have this this plus minus signature in the numerator or the denominator, right? So perhaps it's better to rewrite it this way. And that's the answer. So this is Taylor series standard at 2. If you were to write the first few terms, when n is equal to 0, you have negative sign here, negative 3. When n is equal to 1, you have positive sign, 3x minus 2. When x equal to 2, you have minus sign, 3x minus 2 squared. And it's simply alternating. Okay? All right. Part 2. Any reasons? Part B. Part B, you go, well, I don't want to do this. Right? And I do, what do I want to achieve? I want to write it as a series in x minus 2. Is that right? So in other words, let me call x minus 2 just for clarity. Just for clarity. Let me call this u equal to x minus 2. That will mean that x is equal to u plus 2. Is that right? Okay? Yeah?
I have a question.
Sure.
I don't know how can you change the denominators from the last one.
If you have 1 over negative 1, isn't that the same as negative 1? right? You know, so it doesn't matter which parts, 3 is still the same, right? Okay. You can still use this note. You know, this is perfectly fine. So. All right. So here, even though you don't have to do this, but I think sometimes it's worthwhile if you just use a nice notation. That will help you anchor the thought. So really, I want to write this function as the sum of a series, R series in x minus 2. Now this x minus 2, I give it a simpler notation, u. So u means x minus 2. Then x means u plus 2. Right? So this is 1 minus x is u plus 2. So let me clean it up. Wait a minute. Oh yeah, that's right. Okay. 3 and then negative 1 minus u. Did I do it right? Right? Okay. And then may I absorb the minus? May I change sign top and bottom? So wouldn't that be that? Right? Isn't this one simple? Right? Isn't that negative 3? This is negative 3 over 1 minus negative u. Is that right? Okay, so it's a over 1 minus r. So it's geometric series, sum of geometric series, leading term being negative 3, common ratio being negative u. And so minus 3 plus 3u minus 3u squared plus 3u cubed minus etc. Okay? And then finally, you recall what is u. U is x minus 2. That's what u is. So 3u means 3 times x minus 2 minus 3x minus 2 squared plus 3x minus 2 cubed. Isn't that the same thing? Isn't that the same thing as this one? Right? You can use sigma notation. I'll leave that to you. The same answer. So that's what I mean. This is one of those cases. It's possible to take derivative repeatedly and still manage to get a closed form. All right, this is one of those cases. Just like sine x and cosine x in the Maclaurin series, if you really, if you go from the original definitions of Maclaurin series, then that's how you construct it in the first place. Okay, but most of the functions probably don't want to do that, and so this one you can do either way. Use the definition of Taylor series, or you use some other techniques like geometric series, which fits into this problem. But then you have to do some algebra. So you have to do a little bit algebraic maneuvering in order to make it work. Next question is very similar. You have this simple function f of x equal to square root x. You want its Taylor series centered at 16, and you want to do it in 2 different ways. The first is to use the definition of Taylor series centered at